fallacy number 7. Transport cost isn't a problem. Now, important to understand, on top of the transport cost itself, there's this thing called serialization, deserialization, all right? We talked briefly about that in the network reliability elements on the latency part, saying in addition to the network itself, there's a bunch of preparation work that we do before a call goes on the wire, and a bunch of work that we do after the call gets pulled from the wire until our custom code gets invoked. That serialization and deserialization takes a bunch of CPU time. The bigger and the more complex the data structure that you're moving around is, the more that serialization, deserialization takes. The issue with serialization, and I'm just going to use serialization, not deserialization, otherwise we'll be here all year, is that for the most part, it's not happening in code that we measure. So most of our controllers or service boundaries, all of those things get invoked after the deserialization's already been done. We usually don't profile how long the serialization or the deserialization take. It's something that you should measure if users are complaining that the system is slow. The thing is, for those of you that are on the cloud, that CPU time can actually add up to be quite a lot. Because a lot of our business logic actually isn't really that performance intensive in comparison to a lot of the crazy serialization, deserialization stuff that happens. So if you're in a cloud environment, consider that every remote call that you're doing, in addition to paying for the bandwidth of getting this stuff from one machine to the other, you're paying a big CPU cost as well. One of the things that personally I like the most about the cloud is that at the end of the month, or whatever your billing period is, you get a bill across all the services that you're using that says, at the bottom line, this is how stupid you were when you designed the system. In a way that kind of is incontrovertible. I mean, two developers can argue over the quality of a given design. But if AWS says, at the end of the month, you owe us $75,000, you're like, oh my God, how did that happen? And it'll show you the detail of all of the things that you used. It's one of those elements. It's a harsh reality that all of us are like, oh, okay, can we afford to run this system anymore? Are we making enough money off of the system in order to pay for all of the cloud hosting costs? Yes?
I've had a different thought about that, that sometimes just the cost factor is affecting your architecture.
Mm-hmm.
Because it will be more expensive to do it the right way, and cheaper to do it the wrong way.
Okay.
The more you things together, the cheaper it gets.
Okay. So it hasn't been my experience that doing things the right way is more expensive and doing things the wrong way is less expensive. I think there's a certain element of, let's call it, a violation of the first law of distributed objects, meaning that if the right way means creating lots and lots of little microservices that talk to each other remotely, yes, that ends up being expensive. I challenge that being the right way. I'd say that first and foremost, we should focus on logical decoupling, as we talked about over here, even in advance of us moving to the physical separate deployment. And even if we deploy things separately, they can be different processes running on the same machine. So there's a gradient of different levels of physical isolation that we can create. I wouldn't say that any one of them is necessarily the right way or the wrong way, but starting with a better logical decoupling, in my experience, ends up giving us more leverage and more options without requiring us to go to the big deployments right away. In many cases, the use of queuing technology by encouraging a more asynchronous mode of design creates the possibility for, think of it as sort of different engines that are running in parallel with each other. So we're able to do more parallel processing, which can give us a higher performance, a shorter time to complete an overall workflow than the equivalent synchronous blocking request response model. So I'm not sure I'd agree with doing things the right way is the more expensive model. That hasn't been my experience. Yes, Albert?
Sort of what I've heard here in the room is that monolith equals evil, and I'm not quite buying into that. To a certain degree, I agree if you have too big of a monolith and if it's causing you trouble. But at the end of the day, at this moment, the monolith is paying our salary, and
yes,
it's doing a lot of good. So
right.
If you have trouble with your monolith, then it's time to split it. But I think that as we see here, splitting just for splitting is creating all kinds of different problems. I very much agree that separating out your APIs and stuff like that is always beneficial. At least if you don't get into creating interfaces on your domain model just for the heck of it or something like that.
Right.
But I kind of resent the sort of equality sign between evil and monolith just outright.
So I think part of the problem, and both your comment and the previous question underline that, is that we tend to follow a model where the logical and the physical are one-to-one. So I think that they don't have to be, and we'll talk a lot more about that as we go forward. But as we talked about in this case, we can take what was previously logically monolithic and turn that into more modular pieces logically, and still do a monolithic deployment, meaning taking those logically independent pieces and deploying them to the same server farm, etc., same network. So I definitely resonate with your comment that monolith doesn't equal evil. But I'd say the physically monolithic deployment is not necessarily evil by a long shot. A logically monolithic design where you touch one thing and you break a whole bunch of other things is indeed very painful, and it is something that might be qualified as evil, and we'll talk more about that in our fallacies of enterprise computing. But that part of the source of the conflict is, are we talking about logical architecture here or physical architecture? And that'll be a very big theme for us throughout this entire course is, well, what kind of architecture are we talking about? Because architecture itself is not monolithic. There are different elements of architecture, and there are different tools and approaches that make sense for the different types of architecture. So we'll gradually move in that direction. But it's important to realize that as we were saying before, the right architectural model is usually not going to be do everything this one way all the time, or do nothing this way ever. And that there really isn't this strong best practice or anti-pattern that either something is purely good or purely evil. But there are certain patterns that if you're in this context, this is a good approach. If you're in this other context, this other approach might be better. And that's going to be a lot of what we do, is finding which patterns make sense and attaching them to the relevant context. Saying, therefore, for a given problem domain, we can perform a level of analysis that will lead us to say a more optimal solution, both from a cost perspective, a complexity perspective, a maintainability perspective, etc. All right? Now,
just one comment. It's a really good answer. I still think I've seen that if you make the cost be your only guideline, you can go wrong. You can decide.
Absolutely. Taking any one characteristic and saying, we're going to optimize entirely around that thing, exclusive of any other attribute, tends to cause problems in any type of environment.
The cloud, that might be an issue if looking at this, the bottom line.
Right. Absolutely. Yes?
I was just thinking that isn't this a case of different time frames and different types of cost? Because I think we can say it's all about cost. You can get the best architecture should give you the least long term, or in the term that matters.
So,
You could say that the upfront cost might be higher, but the maintainability of the changes will be better, so you get a
right.
better long-term cost.
Absolutely. So, right. So total cost of ownership, or in essence, looking at cost itself as not being monolithic, saying there's the cost of developer time and complexity and maintainability, which is one element. There are the runtime costs of this. Right. Right. I do want to call out one specific other element of transport costs specifically, because this is something that geographically distributed systems can run into problems around. So when everything is running mostly in one data center, then the transport cost is usually fairly capped and unknown. When you start talking about communication happening between data centers, usually those network links tend to be more expensive because it's just harder to get a great deal of bandwidth over long distances. So the longer the distance, the higher the transport cost. So anytime you're looking at a network boundary, understand that not all network boundaries are equivalent, and that anytime you're doing that sort of cross data center call, ask yourself that question: how much does this call cost? How much does it take to move a megabyte, a gigabyte of information from point A to point B? Because that's not constant in your environment. There was one project that I was brought into fairly late where they were using SQL Server replication to keep different sites in sync. And that was a reasonable solution at the time. But the network folks, because they were dealing in an environment that there wasn't always going to be a strong landline link, they needed the system to be able to work well under emergency conditions as well, they created a fallback, or multiple levels of fallback, where if there couldn't be a landline connection between sites, they would fall back either to a cellular connection or to a satellite connection. Now, obviously, they didn't own those networks, and after a very bad winter, the SQL Server replication happened at least several times over both the cellular network and the satellite link. And then at the end of the month, they got the charge from those providers, and in essence, their cash flow hurt very much at that point in time. And it was that moment where it wasn't clear that we can actually afford to continue to run the system anymore. That if it continues in this way of cellular and satellite connection, this model is not actually going to be financially feasible anymore. You don't want to be on that system where they pull the plug and they say, we can't afford to run this anymore, and you're in your next interview telling about the last system that you just worked on. So it was extremely scalable, but they had to pull the plug. Really? Why? Well, they couldn't afford to run it anymore. It doesn't inspire a lot of confidence in the architect that designed the system. All right? So watch out for transport cost, because it often has that sort of exponential element to it as you're operating on larger and larger links. Okay?